In this video, we're going to look at special triangles, special right-angled triangles, and we're going to look at those triangles to find the side ratios of those triangles, which I'm going to suggest would be useful to memorize, to actually learn, so that you can quite rapidly get to answers to some basic trigonometric problems. Now, I think what I'll do is I'll just immediately draw the triangles that we're going to be dealing with. So if I draw some axes here, there we go, over here and here, and set up some angles. So if I use an orange pen for my triangles, and I'm going to superimpose these over these angles. So all of these, of course, are 90 degrees. 90 degrees is a very important angle, one that we'll be talking about in a later video. But what I'm going to look at is triangles. So in other words, shapes that have 3 angles and 3 sides. And we make those shapes by closing up this angle here. So I'm going to close it up by 1/3. So that would be about here. So in other words, my triangle is going to go from here to here. Hopefully that's straight enough. And this is going to give me a 60-degree triangle. Okay, so from 90 degrees, closed it up so that I've now got an angle here. There we go, of 90 degrees. Sorry, not 90 degrees, 60 degrees. Okay, so here's my 60-degree angle. And if I drop a vertical down here, that completes the triangle. And we're going to use Pythagoras to find out the ratios. Okay, so there's my first one. We'll call it a 60-degree triangle. Okay, let's label it A. My second triangle then is going to be, well, let's close the angle up a little bit more. So from 60 degrees now to 45 degrees. Drop our vertical down here. There's my right angle then, and this angle is going to be 45 degrees. Of course, you'll know that this is going to be 30 degrees because the angles of a triangle add up to 180 degrees. And this is going to be 45, just like this angle. So this, in fact, is going to be an isosceles triangle. So there's all sorts of other things we can say about these triangles, but we're just going to concentrate on the length of the sides for this tutorial. Okay, so 60-degree triangle, angle, and a 60-degree triangle, if you like, 60, 30, 90, we should say. 45 degree, we're going to have here a, close it up even more, a 30 degree, so that's going to be a 1/3 here, like that. So there's our 30 degrees. And finally, whoops, let's just redraw that. Finally, what we're going to look at is a 15-degree. So the 15-degree actually is sort of going to be quite difficult to draw. It's going to be something like that. There we go. Whoops. My drawing is not working very well today. Let's have another go. So I need to do this carefully because it's got to drop from here inside that arc like that. There's my right angle, and I need to draw my baseline here. Okay, good. Now, how am I going to fit my angle in? I'm going to write 15 degrees and just do an arrow like that. Okay, so it's 15 degrees in there. That might be quite extreme, but it'll be fine. It'll serve to show the point. Now, what I'm going to do is show you what these ratios are, and I'm going to use Pythagoras to do that. Let's write first of all what we've got here. So we've got a 60-degree triangle, but let's say, well, what do we know about 60-degree right-angled triangle? One thing we do know, and that, you know, most people just discover by using geometry, is that the side here, which is going to be length 1, let's say, so let's just call it a unit length of 1 from there to there, that's going to be half the hypotenuse, if you like. The name for this diagonal is a hypotenuse. So that's going to be 2. In other words, whatever the lengths of these are, they're in a 1:2 ratio. And we can write that ratio. Let's write it here. 1:2. It's the shortest side in the ratio of the shortest side to the longest side. So 1:2, shortest to longest. Okay, so the question now arises: what's this length here? If we like the height, or this middle length here. Well, the answer is √2. How do I know it's √2? The answer is Pythagoras. Pythagoras tells us that c squared equals a squared plus b squared. And of course we know that a is 1. Okay, and c is 2. Oops, let's just erase that. There we go. C is 2. So 2 squared equals 1 squared plus b squared. So b squared must equal 2 squared subtract 1 squared from both sides. So we've got 4 subtract 1. B squared equals 3. Therefore, square root both sides. B must equal the square root of 3. Like that. So this is the important thing to remember. We've got a 1:2 to √3 triangle. Our proportion for a 60-degree triangle, 60, 30, 90-degree triangle, is 1:2 to, not to 3, which would be very easy to remember, but pretty easy to remember, to √3. Okay? And now what I'm going to do is I'm just going to highlight that, because I do think this is very straightforward to remember. And if you don't have to do the Pythagoras to derive it, then life is a lot easier. Just much, much quicker. So let's erase our workings out and just work with 1:2 to √3. Okay, but if we forget, just go to Pythagoras and you should be able to work it out for yourself. So 1:2 to √3 triangle, we could say, is a 60-degree triangle, 60, 30, 90-degree triangle. Now, what kind of problem are you going to get with this? Let's just do a quick problem, I think. Let's say, so problem A, let's say they give us, they don't give us any of these lengths here. They give us very different values, and they only need to give us one. So what's likely is they're going to give us something like, well, let's say 11. Okay, so the short side is 11. Well, all we need to do is remember these proportions, write them down, write them on the triangle, just as we did just now. 1 to 2, because 2 is going to be the longest side, to √3, which is this side here. Or if you want to do them in size order, which is probably quite a good idea, let's just change them around to 1 to, okay, there we go, 1 to √3 to 2. That's a good way of remembering that 2 is going to be your longest side. So 2 is this one here. Let's just jot it down. So in an exam you might want to just jot down what the figures in the ratio are. So we've got a 2, and this is the shorter one, 1, and the middle one is √3. Okay, I just do those very small now. But that's what we've been given. We've been given in this problem 11. Well, if we've been given 11 for the shortest side, let's use our red here to make it clear. So we've been given 11 for our shortest side. So what's happened to that one? It's been multiplied by 11. Therefore, this must have to be multiplied by 11 because everything's in the same ratio. It's all proportionate. Okay, it's another word for this is similar triangles. So whether the triangle is large or small, the ratio is going to be the same. So everything has got to be multiplied by 11 in this case. So that's going to be 11 times root 3, which we just say is 11 root 3. Keep it in exact form. And 2 times 11 is going to be 22. We've now got our answer. If they asked us, well, let's say they asked us to find this side here, which is L. Or maybe they asked us to find this, which they're calling M. They might ask us to find both of these. So L is very straightforward. L is just 22. Let's give them the answer for M here. So M has got to equal 11 root 3 centimeters. If they want it in decimal form, okay, so what they're going to have to accept is not an exact answer. So we're only going to get an approximate answer here. It's going to be 11 times root 3. Well, what's root 3? It's approximately equal to 1.4. No, it's not. Sorry, it's 1.7. Okay, 1.4 would be root 2. Okay, so root 3 is going to be about 1.7. These are approximate values. So just two significant figures. So 11 times 1.7, well 10 times 1.7 would be 17. So 11 times 1.7 is going to be 18.7. There we go. So there's the answer. M equals 18.7. So that's just an example of the sort of exam question that you might get. But it's using this idea, the idea that this is in proportion or in ratios of 1 to 2 to root 3. Or, if you want to do it in size order, from 1 to root 3 to 2. And it's easy for us to remember these and therefore to get that answer quite rapidly. Okay, let's move on then to our 45-degree triangle. So B, it's going to be our 45-degree triangle. What are the proportions of sides here? Well, again, fairly easy to work out using Pythagoras, so you don't really need to memorize it, but it's a good idea if you do. So this side is 1, this side is 1, let's say. That's always a good idea to start with 1 and then you can see what's going on. So we've got a 1 to 1 already relationship within the 45-degree triangle. What's the other side equal? Well, by Pythagoras, c squared, that's the hypotenuse, equals a squared plus b squared, so that's 1 squared plus 1 squared. In other words, c squared equals 2. Therefore, c must equal root 2. So our ratio is 1 to 1. Whoops. Let's erase that. 1 to 1 to root 2. Okay, and we'll just erase our workings. Okay, 1 to 1 to root 2. Okay, root 2 is about 1.4, so 1 to 1 to about 1.4, or in exact form 1 to 1 to root 2. And it's exact form that you want to remember, because if you're scaling this up, then any inaccuracies are going to also magnify, and you're not going to get the right answer. So keep it in exact form if you can, and only convert at the last minute if you have to. Okay. So what kind of problem might we get where this would be useful? Well, if we think of something like, let's say they give us this side this time, and let's just keep it simple. Let's say they give us this side as 1 centimeter. Okay. Let's keep all our measurements today in centimeters. But it could quite easily be given in kilometers or anything else. But all measurements in centimeters for these particular problems that we're working on today. Okay, so 1. Well, if that side is 1, then these certainly aren't going to be 1, but the proportions are 1 to 1 to root 2. So what's happened is that our root 2 side, this one here, has become 1. Okay, so what has had to happen to root 2 to make it smaller, in fact, than root 2? Root 2 is about 1.4, remember. To make it smaller, it's had to be divided by root 2. And we can, if you're not sure about that, because this can confuse people, if we say, well, to get to 1, what's happened to root 2 to get to 1? Well, we can say that something times 1, okay, 1x, gives us root 2. Sorry, wrong way around, isn't it? I keep making mistakes today, never mind. So, it is easy to get confused here, actually, so it's good to keep these sort of mistakes in the video, because mistakes are how we learn. So in fact it's root 2 times x gives us 1. So in other words, what is x? X has got to be 1. Divide both sides by root 2 and you've got 1 over root 2. Okay, so that's what's happened. It's been divided by root 2 or multiplied by 1 over root 2 to give us 1. In other words, the other sides must also be 1 over root 2. Okay, 1 times 1 over root 2 gives us 1 over root 2. So our side lengths now, let's just do this clearly, are going to be, well, let's say they wanted this side, let's say that was P, or they wanted this side, which is Q, or maybe they wanted Q and P. Depends on the question. But our problem is solved, okay, by saying, well, what's happened here? To get to this 1 here, it's been multiplied by 1 over root 2, so we end up with 1, which is root 2 over root 2, and then we've got 1 over root 2 for P or Q, and 1 over root 2 for Q or P, I suppose you could say. Therefore, P equals 1 over root 2 centimetres in exact form, which is approximately equal to, well, what is it? 1 over root 2 is 1.4, and you could say very quickly that if I multiplied top and bottom by 5, I would get 5. Well, 5 times 14 is 70, so I would get 5 over 7. Okay, so 5/7 of a centimetre. And you could convert that to decimal, but I think as a fraction that's perfectly good enough. So we've got 5/7 of a centimetre. Does that sound plausible? 5/7 of a centimetre and 1 centimetre. Sounds about right, because these are going to be smaller than 1 centimetre. Good, so that's problem B, based on our discovery that the proportions of a 45-degree right angled triangle, or right triangle sometimes called, are in the ratio 1 to 1 to root 2. And it's good, as I said, to remember that. Alright, what happens with our 30-degree triangle? Well, our 30-degree triangle must also be in the proportion, in the ratio 1 to 2 to root 3 to 2, or 1 to 2 to root 3. So that's good news. There's nothing new for us to remember here. Okay? We must have the same proportions. We can write it in a different way if you like. 1 to 2 to root 3. But we know, so I think what I'll do is box it, but box it in a different colour. Okay, just like that. We know that we don't have to memorise anything new here. So a 30-degree triangle is the same as a 60-degree triangle. It's just lying down, if you like. So let's think of a problem that might be given with a 30 degree, let's see, B. Well, if we were given 30 degrees and let's say this side length was 3, let's just give it, that should be fairly straightforward. So this side length is 3 and they've told us that the angle is 30 degrees. So immediately we know it's a 1, 2, root 3 triangle. Okay? So what we need to do is identify which side is the given length 3. Well, that's our middle side. So our middle length is going to be this root 3. Okay? So going back up here, let's use purple again, just to make it clear that it's just the workings. We've got something happening to root 3. It's multiplying by something, an unknown, we'll just call it x, to give us 3. What's happened then to get this 3? X must equal 3, divide both sides by root 3, and you get x equals 3 divided by root 3. Okay? Good. Okay. Now, in that case, we know what's happened to this side. Let's just do it over here to get 3. It's been multiplied by 3 times root 3. Well, all the sides must be multiplied by 3 divided by root 3, 3 over root 3. So in other words, this side must be 2 times 3 over root 3, which is 6 over root 3. And this side is just 1 times 3 over root 3, in other words, 1 over, not that 1, sorry, 3 over root 3. There we go. So these are the new values of our sides. Now something a little bit interesting happens here. Let's say they want us to find, I don't know, let's say the longest side here. So let's call that R, which is quite appropriate because this would be the radius that we use when we draw this arc. Okay, radius of the circle. So if R equals 3, if this length here equals 3 and the angle is 30, then what does R equal? Well, R is this middle length here, so R equals 6 divided by root 3. Now I say that something interesting happens here because we don't generally leave a surd in the denominator. We rationalize the denominator, and that means we just don't we multiply it by another surd so that we don't have a surd in the denominator. We keep the value the same, but we just enlarge this by multiplying by a surd. So the surd that we multiply by is going to be root 3, because root 3 times root 3 will just be 3. And if we multiply the bottom of a fraction, the denominator, by any value, in this case root 3, then we must do the same to the top, the numerator, if we want to keep the value the same. This is just multiplying, in other words, by 1. So now we just multiply out. 6 times root 3 is 6 root 3 divided by root 3 times root 3, which is 3. And 6 divided by 3 is just 2. So our answer is 2 root 3 centimetres. If they want it in decimal form, then we just say 2 times, well, root 3 we know is 1.7, approximately 1.7, and so 2 times 1.7 is going to give us 3.4 centimetres. But this is approximate. Our exact value is exactly 2 root 3 centimetres if we want to keep it in exact form. Now finally, I'm going to just show you what happens when we've got 15 degrees, although I suggest this isn't one that's very easy to remember. It is, though, in surd form, and so it's quite nice to learn it, and if you want to learn it, by all means, please go ahead. What we've got here is the shortest side is very short indeed, and the value of that is it's going to be about, well, if we set the longest side to 4, so the longest side is going to be this hypotenuse, so that's going to be 4. The shortest side here is going to be a little bit short, sorry, not the shortest, this side here is going to be a little bit shorter than 4, and it is approximately 3.9, but we don't want an approximate value, and there's our problem. We can't just write 3.9 because that won't be good to work with, because with ratios, of course, we have to be exact. Now, there is an exact form of this in surds, and it's actually pretty easy to remember. I'm going to rub this out just so that you can see clearly. Let's just write that more clearly. The exact form is root 6. Now, what's root 6? Well, root 6 is about 2.5. You can work it out and check it on your calculator. But the square root of 6 is about 2.5, so about 2.5. And if we add then the square root of 2, we know that the square root of 2 is about 1.4. So 1.4 to 2 significant figures. So if we add the square root of 6 to the square root of 2, we add those together, we are going to get roughly 3.9. 3.9, as I say, isn't the exact figure, but root 6 plus root 2 is. And if we work it out by Pythagoras, this is going to be exactly what we get for the middle side. Now, the short side is also easy to remember, because root 6 plus root 2, I don't think it's that difficult to remember. All we do to get the shortest side is going to be, it's a little bit more than 1. It's about 1.1 when this side is 4. But it's exactly root 6, which is, as we see, about 2.5, minus root 2. So it's a kind of repeat there. Okay? But this time we're subtracting. Now, if it's about 3.9 and root 2 is about 1.4, then 2.5 minus 2.5 then minus 1.4, we've got about 1.1. So you can see this is about 1.1, this is about 3.9. But it's exactly root 6 plus root 2, and this one exactly root 6 minus root 2. So we've got our ratio. Our ratio can't have a 1 in it, which is why it's a little bit more difficult to remember. Our shortest side, if we write that one first, is root 6. Take away root 2. Our next in size order is going to be root 6 plus root 2. And finally, our longest side is 4. So if you can remember that, root 6 minus root 2 to root 6 plus root 2 to 4, and 6, 2, 4, not too difficult to remember, then that's a really nice shortcut if you come across 15 degrees. But as I say, it's pretty unusual that we need the 15-degree triangle. So mostly, this isn't included in a lot of formulae and diagrams, but it's just a nice one to know, and it can certainly come in useful. So worthwhile learning if you want. Now finally, let's just do a problem then using this. What are we going to do? Let's just say they give us that this side here is 2. Okay? In fact, why don't we just erase these here? Okay, erase everything and just give us the problem as it might be set out. Okay? So, this side here they tell us, let's just get the right ink colour here. Okay. This side here they tell us is 2, and the angle here they tell us is 15 degrees. Let's just do an arrow to point inside there is 15 degrees. Okay, this is going to be a bit tricky, but oh, sorry, I just spotted a mistake. So let's just raise that. That should have been problem C, shouldn't it? So this is going to be problem D. So that's C. Now we're working on problem D. The numbers are going to be more tricky, but basically the idea is exactly the same. We're going to be saying, well, what's happened to that 2 from our base angle, if you like, which is going to be this middle one here. Okay, so not the shortest side, which is this, not the longest side, which is this, but this, which is root 6 plus root 2. Well, what's happened is it's been multiplied by something. Okay, let's just work this out. In other words, exactly the same as before, but this time we take these values, root 6 plus root 2 times x is going to give us 2. So what's x? X must be 2 divided by root 6 plus root 2. Okay? Now, to do the next part, what I'm going to do is immediately work in decimals, in approximations, because to work with these numbers is going to be a bit more difficult. But if you want to work in third form, you can. Let's just, in the interest of time though, work this through fairly quickly. So what are we going to say? Well, they want us to find then, let's say they want us to find this short length here. Okay, so let's call this, I don't know, what did we have before? R, so let's call this S. Okay, so what's the value of S going to be? Well, we know that everything gets multiplied now by 2 over root 6 plus root 2. So this short side is going to be this one here, root 6 minus root 2. Right? Root 6 minus root 2 is the value of S. So that's now been multiplied by, well, 2 and divided by root 6 plus root 2, which all looks very complicated, but actually it's not too difficult to do. So I probably should put, let's just rearrange it, I probably should put my 2 up front here, okay, just to make things a bit clearer. Okay, so we've got 2 root 6 minus root 2 divided by root 6 plus root 2. Okay, now this is what S equals. Let's put our D here. This is what S equals. Okay, so S must equal, well, I'm going to, as I say, make this approximate immediately because otherwise we're going to get into some complicated surd calculations. So approximately equal to 2 times root 6. Well, root 6 is about 2.7. Okay, so to two significant figures it's 2.7, and root 2, well, root 2 is equal to 1.4, as we said before, so 1.4. Okay, and so sorry, what am I talking about? Root, I think I must be getting a bit tired. Root 6 is approximately equal to 2.5, but again, a little mistake, but good job I spotted my mistake, so I get this right. Okay, approximately equal to 2.5 minus 1.4 divided by then 2.5 plus 1.4. Okay, so I hope that's clear. Like that. Well, That's pretty easy to work out. 2.5, we've got 2 times whatever's in brackets here. 2.5 minus 1.4 is 1.1. And 2.5 plus 1.4, as we said before, is 3.9. So we've got S is approximately equal to 2.2 divided by 3.9, and if we want to calculate that out, it's 22 divided by 39. And that isn't a fraction that will divide down any further, so we can simply say that's the answer. 22/39 then of a centimetre. S isn't exactly, but is approximately equal to 22/39 of a centimetre. But the main reason to do that rather complicated, which you probably won't get until you get into more advanced mathematics, but working this out shows you that even with something like 15 degrees, the same principles apply. The main thing, though, to take away from this tutorial are these special triangles here, the 30 and the 60 degree triangles, which always give us a 1, 2, root 3. So when it's 30, 60, 90, always gives us a 1, 2, root 3, or 1, root 3, 2 ratio of sides. So worth remembering. And the second triangle that's definitely something that you should understand and memorize is the 45 degree triangle. 45, 45, 90 degree triangle, which will always give us 1 to 1 to root 2 side ratios. Now, what we're going to do in the last part of this video is work through a Pythagorean proof, in other words, a proof of the Pythagorean theorem. And to do that, what I'm doing is borrowing from a proof worked out, in fact, by the, I think it was the 20th President of the United States, President James A. Garfield. But it was very popular to work on Pythagorean proofs, and this is a diagram that he used to do it. Now, what you'll notice from the diagram is that it's made up of the triangles that we've been looking at, these special triangles. So we've got here a 30 degree, 60 degree triangle, okay? And we've got another one here, 60, 30. Okay. This one here is a 45. 45, 45, 90. Whoops, not 44, 45. 45. Whoops. I don't know what's going on here. I must be getting tired. There we go. So, this is the diagram that apparently he used to work out his proof. It's actually much easier, though, if we double his diagram like this, and then I think we can see much more easily what's going on. So what have we got? We've got a Pythagorean. We're working on the Pythagorean theorem, and we're working on a proof. There we go. So to work on a proof, we want to have two ways of looking at this. The first way is, well, let's have a look at these 30, 60, 90 triangles. We've got 4 of them. So if we start by saying there are 4 areas, and the area of a triangle is the 2 side lengths multiplied together, just like with a rectangle, but with a triangle it's half of a rectangle, so it's going to be 4 times a half of A times B. And that gives us the combined areas of the 4 30, 60, 90 triangles on the outside. To get the inside, we don't need to worry about the triangle. We've got 2 45 degree triangles. In other words, we've got a square, so it's just C times C. In other words, C squared. Okay, so that's the area of the square in the center plus the area of the 4 triangles on the outside. Now, to look at it in a slightly different way, well, what have we got? Altogether, we've got a giant square. And that giant square has a side length of a plus b. A plus b. And if we square a plus b, then we must have the whole area then. So 4 times a half ab plus c squared must equal a plus b squared. Now 4 times a half is 2. So we've got 2ab plus c squared equals a plus b squared. Next step, we subtract 2ab from both sides to leave c squared on its own. So our target, remember, is c squared equals a squared plus b squared. So we want c squared on the left-hand side. Subtract 2ab from 2ab. Well, that's cancelled it from the left-hand side. And we end up on the right-hand side with a plus b squared. Subtract minus 2ab. Therefore, c squared equals, well, all we do now is expand out this a plus b squared. So if we expand that out, we've got a plus b times a plus b. If we use foiling, first, outer, inner, last, then we'll have a squared plus the outer and inner will give us 2ab, and the last will give us b times b, so b squared minus 2ab. Well, look what we've got. We've got 2ab minus 2ab. So if we commute these, we'll just straightforwardly cancel them. 2ab minus 2ab is 0, and we've got our proof. So we've got c squared equals a squared, and here we've got plus b squared. So there's the proof, or a proof, one proof. There are many others, and you might want to look them up. They're also just visual demonstrations of why the areas c squared plus a squared plus b squared equate in this way. But that's a proof, and it's nice to know that it is true. It's nice to know why it's true, and it might be something you want to learn. And the other